Hello, this is Karakuso from Cardiff School of Computer Science and Informatics. Firstly, I'm really sorry that I can't be there with you during this great workshop about Earth observation. But in 2025, some people still having problems with visa to travel for research purposes. It's a shame, but nothing to do. Thanks for workshop organizers giving me this opportunity to present this offline. And for any of your questions, I will be ready for your emails or anytime you can reach me out. So let's leave the politics one side. This topic, in collaboration with my colleague Porrick Corcoran from the same school in Cardiff, entitled as a multi-modal spatial risk framework for electric vehicle charging infrastructure using remote sensing. Our motivation starts with actually the existing electric vehicle charging infrastructures, and there are some problems on that. Currently, especially with these new regulations from the governments, electric vehicles and their usage getting increased quite a lot. So, but the infrastructure in parallel with that, it's also expanding rapidly. However, the infrastructure remains vulnerable to currently changing climate problems and also some other network stressors. When we checked the literature, we realized the current models mostly focusing on where to locate the electric vehicle charging stations, but they generally ignore the environmental risks on the charging stations. So here our target is to use remote sensing data which can enable a scalable data-driven vulnerability analysis. For this purpose, we propose RESERI EV, which is called Remote Sensing Environmental Resilience Index for electric vehicles. So our framework targets to integrate multimodal spatial data layers coming from different sides of environmental and also infrastructure details. For example, flood risk, heat-related risks, vegetation problems, infrastructure proximity like grids and roads, and also we are adding some graph topology to this game to make it more reliable. So we try to compute a composite resilience score per station. The main target is to quantify the risk, to map the resilience, and to guide infrastructure. All right, so I mentioned that our target is to use lots of remote sensing data and bringing together different layers. So what type of data we are using in this proof of concept work? The first is, of course, electric vehicle charging stations data, which is coming from Open Charge Map source, giving us very rich data in terms of locations, types, and status of the chargers. And of course, the main target was to use remote sensing. So here we are using Landsat 8 land surface temperature data, and from Sentinel-2 mission we are using NDVI data to roughly analyze the environmental data. And also we have flood risk shape files. So in this paper we focused on whales only. But this can be scaled up very easily. Of course, when we focus on whales, the data is coming from environmental platform Whales for this. So this platform is providing us with sea-based and river-based flood risk of the areas in the whole Wales map. And lastly, we are also using infrastructure details, so substation proximity and road network accessibility by using OpenStreetMap source. Okay, after looking at the types of data we have, so in order to create our resilience index, we are taking all these data and creating different types of risk layers in the end to be combined as a final resilience index like value. So here we are using the risk layers, firstly coming from a little bit climate related things, for example flood risk, whether the station is in a flood zone or not, and land surface temperature risk. If you if you think that all these chargers are highly electronic devices, they are their productivity are getting affected by very high or very low temperatures. For that reason, we are looking at these kind of risks if the chargers are under risk or not. And some infrastructure related details from the grid and road. So we are looking at the station, the distance of the station to a substation, and also we are looking at how the access to major roads from the charger. Lastly, the environmental factors coming from vegetations and land use, land cover. So this data provided from remote sensing, and we are using these data to create another risk layer. I mentioned previously, this is a proof of concept work for us right now. And our bigger target is to use graph theory related calculations and also graph neural networks in the later stages as the future work. So currently we started to use the graph construction with a fundamental k nearest neighbor graph that connects 5 nearest neighbors. Here the nodes are the charging stations and the edges are the nearest neighbors to them. Then, in order to calculate the index, resilience index, we aggregate and normalize the indicators. As for the proof of concept, we used right now equal weights for each flood risk, but this can be changed according to their sensitivity in the future work. As you might imagine, some risks are more important than the others for the chargers. So we will take this into consideration in the future work. And we also excluded some incomplete data to preserve integrity. Now I'm passing to the results. So there will be a couple of slides in terms of the results. So I firstly would like to show you the generic results in terms of the layers we investigated in this work. According to the results, we realized that more than 70% of the stations are exposed to high land surface temperature risk. This is more than our expectations, to be honest, but it is also a good sign to investigate the infrastructure problems. Along with that, more than 50% of the more than 50% of the stations are under vegetation stress. And we realized nearly 89% of the stations currently is under at least one risk layer. Then in the second table, we combined some risk layers to see, and here one important result might be shown: land surface temperature and vegetation risks combined, affecting 40% of the stations. So this is a little bit detail. So in the previous one we showed only two layers, but here in this bar, very basic bar graph, we are showing the stations with their number of risks, and here you can see that more than 50% of the stations are under 2 and more risks. So here 2 is the top, a high number, and there are some stations 3, and even there are some stations under 4 different types of risk layers. This is the Pearson correlation heat map. So this is highly important for us because we are bringing together all these layers, but we are also wondering how correlated these layers are. This is showing us the correlation between the layers are very weak, and this also supports our target to use this multimodal approach. Probably the highest correlation can be seen here between the road and grid map as the 0.20, and similarly grid and road here the same, and this is showing us a good sign of using the multimodal data for this kind of analysis. So let's look at a little bit the map versions. So here we are showing 6 different versions of Wales. So in the first one, all the charging stations. This is the flood risk, red showing high, green showing low risk, and this is land surface temperature. This is highly important that you can see, especially Cardiff, Vale of Glamorgan, Newport, and the valley areas here, Swansea, and some and also the north part, Bangor, Wrexham area is getting affected by highly land surface temperature problems. Grid proximity and road proximity looks quite good. A very small number of problematic charging stations exist. And in terms of vegetation related to the land surface temperature, again, here we are having lots of problems in the especially urban areas. This is the final result showing the distribution of our average resilience index score in this map on the right. So you can see from the color bar, greenish the color is showing the low risk, and reddish is showing a high index. So similar to the one I showed you before, the Cardiff, Vale of Glamorgan, Swansea area, and also the north part is like Wrexham, Bangor area, showing a little bit higher risks, and also some coastal areas, even in the low risk regions, some coastal areas also showing high risk, potentially caused by the sea-based flooding risks. When we look at the distribution of the low, moderate, and high risks here, we can clearly see that mostly moderate risk we have for the areas, but we also have some problematic areas here mentioned. All right, so I would like to conclude. So our index enables scalable and interpretable climate risk screening. Graph view supports spatial reasoning and future network analysis. As I mentioned, this is a proof of concept, so we will improve this by using a very advanced graph usage. And we are proposing some modular framework extendable to other geographies and dynamic scenarios. In the future work, we will extend this to predictive simulations, some what if scenarios, counterfactual reasonings like works. Thanks for your attention. As I mentioned, these are our email address on the slide right now. You can reach both me and Porik for this. I would like to thank you on behalf of my research group in Cardiff Remote Sensing, Image and Data Analysis RESIDA group and Cardiff School of Computer Science. Thanks again for giving me this opportunity. I am ready for your questions anytime if you want to send me. Thank you.